Hi there, Science 10. We're going to cover a couple things today. One is I'd like to revisit a worksheet I started the other day on energy, kinetic and potential energy. And the other is we're going to look at lesson 3 on nuclear reactions. I have a little bit of a demonstration for you, and you'll see a worksheet popping up. So this will be down as this lesson right here, 3, nuclear radiation for the worksheet. There will be some decay equations that I suggest you fill in that I've written on the board. But first of all, let's look at that worksheet. My gut feeling is probably a few of you have had maybe some difficulty with that, if I was to make a guess. And there's one problem at the end of the worksheet that I was thinking, well, I think they'll be able to do that, but maybe with a bit more support. The problem is to ask you, what is the height of the world's tallest tree based on some information that you're provided about kinetic energy. Specifically, you're provided with the information about how much energy a weight has gained just before it hits the ground when it's dropped from that tree. Obviously, when something hits the ground, it stops, so kinetic energy goes to nothing. That energy has been transferred to the ground, but just before it hits the ground, it's going really fast. And that speed it has gives it kinetic energy. And that kinetic energy, the unit for it, is the joule. So, and that's capital J. But the other thing to remember is that energy can't be created or destroyed. You can only change forms of energy, and this is especially important for this problem. For analyzing this problem, because it actually makes it a lot simpler, is what I'm trying to say. Let's imagine a different problem. Imagine the CN tower, similar situation. You have a 1 kilogram weight, maybe a little ball of metal, and you're dropping it from a CN tower. Just before it hits the ground, it's going really fast. That speed gives it kinetic energy, because kinetic energy equals 1/2 of the mass of an object times the square of its speed. When it hits as it hits the ground, just before it does that, it's going really fast. All of its energy is kinetic energy. And a key point here is that if it's just above the ground, we can as good as say it has no gravitational potential energy left because it has no further to fall. By contrast, just before you release it from the top of the CN Tower, that big building in Toronto, it has no kinetic energy because it's not moving, but it has plenty of gravitational potential energy because it's really high up. It has the potential to gain a lot of energy in falling down, but that gravitational potential energy is stored energy. It's not active energy. We call it potential energy. It's one kind of potential energy. Here's how we can examine the problem. I'm going to zero in on it with the camera. So this is the CN Tower right here. Don't know if you can see it, but this little black spot is a falling object, your 1 kilogram weight. So at the top, kinetic energy equals 0. All of the energy is gravitational potential. As it's falling, the energy is being converted from kinetic to gravitational potential energy. But the total amount of energy is staying the same. The total amount of energy is kinetic energy plus gravitational potential energy, and that does not change. Just before it hits the ground, it's all kinetic and no gravitational. It's just really high because, after all, you dropped it off the CN Tower. Here's the information you're given. For this object, the kinetic energy at impact is 5,420 joules. How high is the tower? You could look that up on the internet. I did. But we can also use that information. If we assume that the kinetic energy at the end equals a gravitational potential energy, at the start, sorry, mistake there. If we assume that kinetic energy at the end equals gravitational potential energy at the start, here's how the problem plays out. We can say that our equation is this for gravitational potential energy, because that's what I've told you. Gravitational potential energy is mass times acceleration due to gravity times the difference in height. in this case, the height of the tower. On the formula sheet, I told you you could rearrange that equation. Height is gravitational potential energy divided by mg. Now, because all the energy went from gravitational potential to kinetic, we can say that when it was at the top, the gravitational potential energy was 5,420 joules. That all became kinetic. Now we start to fill in what we know. How heavy is the mass? What's this mass? 1 kilogram. On Earth, acceleration due to gravity is 9.8 meters per second squared. We take that information and we put it into the equation. I'm going to say that a lot, or I do say that a lot. The height is 5,420 joules divided by 1 kilogram times 9.8 meters per second squared, and that gives you a height of 553 meters, which happens to be the height of the CN Tower. So that's the problem I wanted to review for you. The problem in your worksheet is very similar, and you would solve it in the same way. Today we're looking at nuclear reactions. So far you've been looking at chemical reactions, and those are all about what happens to the electrons. In a chemical reaction, electrons can be shared or they can be transferred from one chemical species to another. Sodium reacts with chlorine, transfers its electron to chlorine. We end up with sodium chloride, table salt. Of course, I don't need to go into lots of these examples because you just did a unit on chemistry, but what I'm leading into is the fact that for nuclear reactions, we're not looking at electrons anymore. We're looking at what happens inside the nucleus of the atoms. And the nucleus of an atom is made of two things, protons and neutrons. Nuclear reactions about what happens to those particles. Nuclear reactions can release staggering amounts of energy. And what they do, the way they release that energy is two ways. One, a nucleus can break apart into smaller pieces. Two, and this is a special case, smaller nuclei can join together. And when you do this, you're kind of, I won't say breaking a rule. Well, in a way you are. You're breaking the rule that the elements you start with should be the elements you end up with. That works for chemical reactions, but it doesn't work for nuclear reactions. In the case of nuclear reactions, you can start with one element and end up with different elements, either by things joining together or things breaking apart, because the identity of an element is decided by the particles in its nucleus. Now, I want to look at 5 different ways that can happen for the worksheet problems. I'm going to describe a little bit about these, and I'm going to give you the best of a demonstration I can give. Now, the way this usually starts is with what's called alpha decay. The decay part means that the nucleus is breaking down into simpler pieces. We have 3 what are called particles, alpha, beta, and gamma. They actually just correspond to the Greek letters of the alphabet. Alpha is A, beta is B, gamma is C. You don't really need to know that. It's just 3 different forms of what are called radiation that spray out from anything that's radioactive. Alpha decay is when a nucleus breaks into 2 pieces. One piece is something with a smaller atomic mass, and another specifically is a helium nucleus. Now, in this case, alpha decay is considered not super dangerous because you can stop it with a sheet of paper. I want to show you something about how nuclear reactions work. First of all, let's look at the top row here. They usually happen with very big, at least nuclear decay, happens with high atomic number elements. Most of the problems you're going to see involve high atomic number elements, like radium and radon. These are both high atomic number elements. Radioactivity was discovered for radium. But what about that number after that? Radium-226. This all comes back to neutrons. Here's the deal. Every element has its identity decided by how many protons are in the nucleus. But the neutrons don't decide the identity of the element, but you have different versions of every element that are and it's decided what version it is by how many neutrons are in the nucleus. So you can have a version of tin that might have, say, 52 neutrons in the nucleus, another one that might have 55 neutrons in the nucleus. The number of protons is always 50, but that other figure can change. And those different numbers of neutrons determine what isotope it is. Different isotopes of the same element, they are different isotopes because they have different numbers of neutrons. The neutrons don't decide which element it is, but they decide which isotope it is. And for nuclear decay equations, you need to say which isotope you're dealing with. In this case, we're dealing with radium-226. If we can imagine a radium-225, that would be different because it would have one less neutron. That number refers to something called the atomic mass, how heavy the nucleus is. And the units for that are the units of a proton. Protons and neutrons weigh about the same amount. I'm going to show you an atomic energy symbol and it's an atomic symbol for an element, and then explain what it all means. Here it is right here. This is the one we're starting with. First of all, for an atomic symbol, we're going to have here is radium. We know it's radium because it's Ra. You can go to the periodic table and find Ra, and I guess that's radium. The 88 for radium, that number 88, is always going to be next to radium because radium is element 88. This number here, the 226, might vary from one nucleus to another because there can be different isotopes of radium. Let's see, 226 minus 88, well, let's see, 226 minus 100, 126 plus 12. It would mean that this one would have 138 neutrons. So 88 protons and 138 neutrons makes up one radium nucleus. And all that information is packed into that symbol right there. Ra, radium. It's got 88 protons, always. This one has an atomic mass of 226. That's determined by it having the 88 protons and 138 neutrons. So that's that isotope. It's an unstable isotope. It can break apart. One way it can break apart is alpha decay. In alpha decay, we lose a helium nucleus. But the law of conservation of mass, at least for the atomic units, we're still going to follow it. Later on in your physics, you're going to learn how there can be very slight violations of that law of conservation of mass, and they have a lot to do with nuclear weapons and nuclear power plants. But at the level of these numbers right here, we're not going to break the law. Here, we're not making, and this is going to come later, but here the protons are staying protons, the neutrons are staying neutrons, and the numbers across the top, the sum of them, will equal the sum of the numbers across the bottom. In fact, that is always true. Look at this. We're making, when this radium nucleus breaks apart, we're making one nucleus of Rn. Well, what's Rn? Go to the periodic table. It's radon. Radon always has an atomic number of 86. This radon is radon-222, so it's got an atomic mass of 222, which means, let's see, 222 minus 86, 122 plus 14, 136. It's got 136 neutrons and 86 protons in that one radon nucleus because the protons and the neutrons are packed together. But in addition to that, there's this thing right here, an alpha particle. There's two ways of saying I've got an alpha particle. Here's one way. That, in the middle right there, is the Greek letter alpha. But more relevant for you guys is this right here in the middle. What's that? Well, that's a helium nucleus, but it's identical, exactly identical, to, when it's alone, an alpha particle. How did it get that symbol? Well, helium is He. Every helium nucleus has got 2 protons and 2 neutrons. So its mass is 4. That accounts for the 4 up there. And every helium nucleus always has 2 protons. So that 2 is always going to go there. You can, if you know the element, you can always fill in that number at the bottom left. This is alpha decay, where we've got a radium nucleus breaking up into smaller pieces, a radon-222 nucleus, and a helium nucleus, and they go their separate ways. And by the way, they also release energy when this is happening. Radioactive decay usually, in fact, yes, will always release energy. Fusion sometimes absorbs energy. Now we're going to look at the next kind. Normally this is dealt with in this order. It's beta decay. Beta decay is different. I'm going to deal just with what's called beta negative decay. In that kind of decay, an electron is being released. But this one's actually pretty cool. Let's look at what happens here. First of all, I'll remind you of a rule. The numbers along the bottom are always going to add up the same on each side of the equation. This side of the equation, it adds up to 3. This side of the equation, well, 4 plus negative 1, also adds up to 3. Because what's happening here, in fact, I want to be more specific. What's actually constant across the bottom is the charge. Electrons are being sprayed away in the case of beta decay. Electrons have a charge of negative 1. This isn't like negative mass, so it's actually charge. So what's actually happening here? Because look, lithium, a lithium nucleus, specifically lithium-8, is breaking up into beryllium-8 and spraying off an electron in the process. Earlier on in chemistry, you learned that neutrons have got no charge. Now, really that's equivalent to a negative charge and a positive charge exactly canceling each other out. In the case of beta negative decay, what's happening is that a neutron is breaking apart into a proton and an electron. The electron gets ejected from the nucleus, and that neutron is transformed into a proton. So look what happened. We went up by 1 for the atomic number. If you look in the periodic table, you'll see that lithium is actually a lower atomic number than beryllium, lower by 1. And so this kind of explains the fact that we've gone up. Because the units across the bottom are actually expressing charge, because of that fact, we've gone up by 1 because what's being released here has that negative 1 charge. If we're dealing with this as an isolated symbol, we can say that this is always going to be identical to the atomic number. But for the purposes of nuclear decay equations, you actually do need to treat that as a charge. And that becomes important when we're dealing with the situation of an electron being released. There's something else called beta positive decay, and something called a positron gets released that you haven't even learned about. It's like an electron with a positive charge, and that happens when a proton becomes a neutron and sprays off this exotic particle. Typical Science 10 level courses, they don't go into beta positive decay, but you should be familiar with beta negative decay. One nucleus breaks apart into a different nucleus, sprays off an electron. It will have the same mass, 8 in this case, but its atomic number goes up by 1 for beta negative decay. Beta negative decay can be stopped. The example normally given is a sheet of aluminum foil. If you have a sheet of aluminum foil, it will stop beta negative decay. Your hand will as well. Whereas alpha decay, they're these big clumsy particles. After all, they're helium nuclei. A simple sheet of paper will stop alpha particles in their tracks. Gamma decay is a little different because there's actually no mass change at all. Gamma decay often happens at the same time as alpha and beta decay, because what's going on is there's a release of energy. Here's an example of gamma decay. We have thorium-234. How do I know it's thorium-234? Because we have Th for thorium, and the 234 is the atomic mass. By the way, this is a situation where, well, thorium is element 90, always element 90. So 90 is always going to go there if you see Th. And the 234 tells us it's got 90 protons, as in always, and 144 neutrons. They add up to 234. On the other side, well, we've still got thorium-234. I didn't do anything different, except I did one thing, and I put this right here. That thing that looks like a letter Y, I don't want to confuse you too much, it's not a letter Y. It's actually the Greek way of saying letter C, gamma. This is a gamma ray. I'd like you to notice one thing. It has a 0 charge and a 0 mass, because it's just electromagnetic radiation. If you thought X-rays were bad for you, gamma rays are really bad. They're also called cosmic rays, and they can give you cancer. This is the reason why you really don't want to be exposed to too much radioactive material. All of us, it's unavoidable that we're exposed to radiation, gamma rays, beta rays, alpha radiation. This happens to us all in our daily lives. It's a constant thing, but you don't want to do any more of it than you have to. Especially consuming anything that's radioactive is really bad. So for gamma radiation, the only thing that changed was this right here. Notice I have a little asterisk next to that. That means like the energized form, the unstable form of that thorium-234 nucleus changes shape a little bit. It becomes the stable form, releasing energy in the process as a gamma ray. Again, this will happen often as a side process when alpha decay and beta decay are going on. But it can also be released in the process of fission and fusion. But before I show that to you, I'd like to show you something else. It's this right here, the nucleus. It's just called the nucleus, actually. The Model 500 nucleus scalar. Some years ago, especially during the 50s and 60s, radioactivity was a big concern, maybe a much bigger concern than it is in culture today, because we had the nuclear arms race. So there were nuclear weapons pointed by Russia at the U.S. and the U.S. at Russia. They're still there. They haven't gone anywhere. They could be launched at any moment, but there's a lot less tension between those two countries now, and so it's not something that's discussed a whole lot. Maybe it should be a lot more. Back then, it was something that was considered much more important to be learning about and much more important to be investigating, even at a high school classroom level. Hence that very old model Geiger counter. That thing is, well, I don't know, 40, 50 years old. I have no idea. It looks really old. And I'll be honest, it doesn't work particularly well, but it still does work a little bit. So what it does is this. It does it not very well, but it actually counts events of beta decay, because and it should do alpha decay as well, but I haven't figured out how to make it do that. And I think it's very possible it doesn't even do it anymore. But it'll do beta decay for you. Beta decay, I hope that this is kind of clear here, is happening as a single event. What that statement is there is that is one lithium-8 nucleus decaying into a beryllium-8 nucleus and an electron. It happens one pop at a time. On a Geiger counter, you'll actually, a noise-based one, you'll actually hear this. Sounds like radio static or popcorn in an oven. Here, it doesn't have a volume, doesn't make any noise. It registers decay events on the screen. Also, what I brought today, you can see right here, is in this little vial this vial right here. This is actually a very unusual vial, because while alpha decay will be stopped by a sheet of paper, beta decay will be stopped by a sheet of aluminum foil. To stop gamma rays, you need a thick sheet of lead. In this case, we have something about, it's about this thick. The walls of it are about that thick, and it's made of lead. And what have we got inside? We have radioisotope samples. There's radioactive stuff inside there. Now, in actual practice, that radioactive material was purchased many, many years ago. And what happens with radioactive material is it becomes less radioactive over time. In the same way that if you take a hot cup of coffee and you let it sit for a while, it'll cool down. You can make kind of an analogy to radioactive material. It's really radioactive for a while, but then it becomes less and less radioactive over time. This is a rule for radioactive material. It's unstable, and it wants to just decay into a more stable state. But at the same time, we still need to treat the contents with respect. I have no intention of touching anything in there or taking any of those things out, despite the fact that you could get more radioactivity with some things in your daily life. I'm not going to touch it, but I am going to open it up. So here's how this is going to go. First of all, put this on. There it gives a whole set of numbers, which I think are more or less randomly generated. Just do the reset. Okay, stop. All right. Should work. Okay, it's working. Good. I'd like you to notice this. The numbers are slowly changing, and the numbers are going up. What it's doing is registering decay events with this sensor right here. Every time there is a decay event that is registered by the sensor, it is then, that information then gets fed into the nucleus account. Now, I know this thing doesn't work because it periodically switches itself off and puts it on to stop, and then it doesn't go up anymore. So it's a really poor quality piece of equipment, but I guess it used to be really good. Doesn't really matter. It still is registering decay events. I'm going to switch it off, put it back on. Here's what I want you to notice. We're at 86 right now, then it went to 87, 88. Now I'm going to remove this lid right here. Watch what happens to the numbers. There. That didn't work out at all. There we are. They're going up a lot faster than they were before. Now we're on stop. So I'm done working with radioactive substances for today. That's it for the demonstration. Not super exciting. What I just showed you is an example of beta radiation. So that's spraying off beta particles. I'm going to show you now fission and fusion equations. Fission is what's created when one large nucleus breaks into two other nuclei with a bunch of neutrons. This is a really dangerous one. It's dangerous because you can make it into a chain reaction situation. It's a little bit like pool being played with balls of very different sizes, because one of the balls, neutron, if it hits an unstable nucleus, like a really big unstable nucleus, hard enough, that nucleus will break into smaller parts. One of the parts that gets sprayed away is neutrons. Now, when you're spraying off neutrons from that's going to hit in a pure sample, that'll hit other nuclei from that same element, and you end up with a chain reaction situation where a lot of energy gets released in a very short amount of time. This is the technology, I guess it's the process, the scientific process that is harnessed for nuclear weapons and also for nuclear power plants. It involves really big atomic nuclei that are very unstable. A little bit like a house of cards. If you ever try to build a really tall house of cards, I can't do it, but you've seen people do it. And it gets really high. The higher it gets, the more unstable it gets, or at least it's a lot easier to knock it over. Maybe not the best analogy, but it still works a little bit. Here's a nucleus. I hope that looking at it with a periodic table by now, you can tell me what we should call it. CF, the periodic table bottom row, is californium. Californium always has an atomic number of 98. That's why there's a 98 there. Some californium nuclei, but not all, have a mass of 252. That would be 98 plus the 154 neutrons that are in it. You'll notice, by the way, that the bigger a nucleus gets, the more neutrons you have to sort of have to stuff into it as a kind of a fluff to keep the protons apart. This explains partly why really big nuclei are so unstable. Those protons don't want to hang out. So californium-252, by fission, can break up into these 3 particles. Well, actually 6. One of them is xenon-140, another is ruthenium-108, and then 4 neutrons. Now, in reality, there's different fission pathways for any element that will undergo fission. They can break into any number of different arrangements of particles, but they always follow the rules of addition across the top, addition across the bottom. Here, look. Californium-252 has a mass of 252. The total mass on the product side here is also 252. Look. 140 plus 108 is 248. Plus 4 neutrons. Well, 248 plus 4 is, it's 252. The numbers across the top must always add up. Notice I put a 4 right here. It's a coefficient. I'm saying 4 neutrons. The numbers across the bottom always add up. Californium, 98. 54 plus 44 is 98. Oh, what about the neutrons? Don't worry about them. Neutrons don't have a charge, so they're not included in that. The numbers across the bottom and across the top will always add up. So this is an example of fission. There's a lot of other examples of fission, and there are actually some that are a lot better known that I put onto the worksheet that you'll be able to work with. Nuclear fusion is another situation entirely. With nuclear fusion, you're taking smaller nuclei, joining them together, and making larger atomic number atoms or nuclei. This explains why the universe isn't all made of hydrogen. When the universe started out, it had a kind of a messy mass of a disordered mass of very hot exotic particles, including a whole lot of lone protons. A proton with an electron surrounding it or orbiting it is a hydrogen atom. Most of the universe is still made of hydrogen, but inside the core of stars, they release energy, all that light energy, because of nuclear fusion. The main reaction happening is hydrogen nuclei joining together to form helium nuclei. You need that to happen not just once, because you've got to make neutrons as well, and that happens through beta decay. Happens through it happens through beta decay. My bad. You've got energy being released in the process. Now, of course, we're not made of helium. We're made of a lot of different elements. We're made of carbon. We're made of oxygen. We're made of calcium. A lot of other chemical elements make up the human body. One of what are considered like the most beautiful insights of science is that we're made of atoms that themselves could only possibly have been made in the cores of giant stars. The sun isn't going to do this very much. Bigger stars will make those high atomic number elements, especially towards the end of their life when the giant star, running out of hydrogen, that source of heat for most of its life, collapses in upon itself until it is a small, extremely hot body with extremely high pressure, extreme conditions that can push the bigger nuclei together. Nuclei don't really want to get together because they've both got positive charges. Say, an argon nucleus and a helium nucleus, they've both got a positive charge. It's like a north and a south pole magnet, or a north and a north pole magnet. You try pushing them together and they want to push apart. And the closer you get them together, the harder they push. With fusion, it's the same way. It takes a tremendous amount of energy to push two nuclei close enough together that they will make one, because they've both got positive charges, which is explaining why it's proving so difficult for scientists to make nuclear fusion happen in a lab situation on Earth and get energy from it, which would be really nice if we could. So this typically, especially for making the big elements, only happens in the core of giant stars. And there's no reason to think that on Earth we'll ever be able to make these high atomic number elements. So here is a situation where we know that our bones have a lot of calcium in them. Where did that calcium come from? One route for making calcium is in the core of old giant stars. There's different star situations it can form in, but it's all in the stars. It's all in the core of the star where it's really hot and really dense, and the particles are moving really fast. How do you make calcium? Well, you can make it with a nucleus of the noble gas argon-36. Electrons aren't in the picture here because these nuclei are moving around without electrons attached to them. But it's still a nucleus of argon-36. And an alpha particle, if they fuse, you'll get calcium. How do I know? Well, let's look at the fusion equation. Argon-36 is this. It's always element 18. It has a mass of 36. Why? Because I told you, 36. It fuses with a helium nucleus, or also called an alpha particle. It's got a mass of 4 and a charge of 2. In this case, here, the charge you can think of as really equivalent to the number of protons, although we always have to think of this in real terms as the charge. The numbers will always add up across the top, always add up across the bottom. 18 plus 2 is 20. Oh, look, we just made element 20. 36 plus 4 is 40. So specifically, we didn't just make element 20. We made an element 20 nucleus that has a mass of 40. Calcium. Calcium-40 is the specific isotope that gets made in this situation. So what it says here is argon-36 and an alpha particle fused to make calcium-40. This is just one example of nuclear fusion. At the same time, though, if you look at the periodic table, everything above hydrogen has to get made by fusion. After all, the universe began with only hydrogen. To go up to any other element, you have to fuse elements together. And this also helps to partly explain why some elements are particularly rare in the universe, especially the higher atomic number elements, because it's harder and harder to make them through fusion. The bigger the nucleus is, the harder it is to push something else into it. So that's a bit about different kinds of nuclear reactions. I've shown you alpha, beta, and gamma nuclear decay. I also showed you fission that happens in atomic power plants with big nuclei breaking into smaller ones and neutrons. And then fusion, which in our universe happens in the cores of very old stars, and explains why we have such a variety of different chemical elements that we perceive every day. I hope this has helped, and I'll be putting up a worksheet for this soon.